Hello, I'm Anna Mackay, and this video in the Integral Calculus series, we will be looking at upper and lower rectangles. Now for my class, we do this at the end of a course, but sometimes it's done at the beginning to get an idea about what integral calculus is really about. So it's about calculating the area under curves. So what we're talking about is, let's have a look at this shape here. If you had to calculate the area of that shape that's created under the curve, well, what type of shape is that? Have a think about that. Could it be a triangle? Well, if it was to be a triangle, we'd have to go from here down to the origin, because let's have a look at what we're actually dealing with. Suppose we wish to estimate the area enclosed by the function, which is x cubed, the x-axis, and the vertical line x equals 2. It's also with the line x equals 0, but that happens to be where the curve meets the x-axis anyway. So what shape is that? Well, if we did a triangle with base 2 and height up to this point, the area that we're going to get is more than we actually need. So what can we do? The technique is to break this shape into some smaller rectangles and use that as an approximation, so that when we come to learn the rules of integral calculus, it works out the exact area of these shapes. All right, so here's the function again, x cubed. As I said, we break it into some rectangles. So let's have a look. We call these the upper rectangles, or an overestimate. So we've got between 0 and 2, and we break it into 4 rectangles. So the width of each rectangle is 0.5. What's the area of a rectangle? Basic formula, base times height. So what's the base of each of these rectangles? Well, as we said, the width is 0.5. So that's fine, and that's going to be the same for each rectangle. But what about the height? Okay, so let's have a look. The height of this rectangle goes up to here. So we could estimate that off the axis, but that's not going to be accurate all the time. So we need a technique. Well, this lines up with 2. When x is equal to 2, it hits the curve there. So what we do is we take x is equal to 2 and we substitute it into the function. 2 cubed will give us 8. As you can see, that's an easy one visually. So the height of this rectangle is 8. So the area will be base times by height, a half times by 8. Looking at the next rectangle, the smaller one, so base is a half and height, well, we can't estimate that one, we have to be accurate. So the height is when x is equal to 1.5. So we substitute that into the formula here and find the answer of 1.5 cubed, and that will be the equivalent y value, and that's the height of our rectangle. So these are over approximations, upper rectangles, and over here we call these the lower rectangles. So hopefully you can appreciate that. Let's look at this section here. Just this rectangle here for the area would be an over approximation, whereas the equivalent rectangle, the fourth one along, would be an under approximation of the area. So between the two, the true area would be between them. You can sort of see that if you take that near triangle looking portion, flipped it on 2 axes of symmetry and put it in that gap, you know, it would approximately be right. And as the rectangles get smaller and smaller at a time, that margin of error will get smaller. So how do we calculate the lower rectangles? Well, the width again is 0.5 each time, and the height, base times by height. Well, the height this time comes from the upper left hand corner of this rectangle, where that hits the curve. So that's 1.5 for x, subbing that into the formula 1.5 cubed. So some of these numbers will repeat, and that's really handy. Let me show you how we're going to set that out. So we're going to have the total area for upper rectangles, and we often call that a subscript u. The formula here, a half each time. You can see that being repeated because that's base times by height. And the height of these upper rectangles we talked about was that the function at 2, so that's this one here. The function at 1.5, that's this section here. The function at 1, and the function at 0.5. And for the lower rectangles, base times by height again. The base each time is 0.5, hence that. And the height of the function each time will be on the left-hand end. So we have the height at 0. So technically that's 0, but sometimes it's a good habit to get used to writing it out for all 4 rectangles. Then you know you haven't missed one. The height at 0.5, at 1 and 1.5. So we're going to go and write this out ourselves so that we get into the habit of doing that. Actually, we're going to go to our calculators, and I'm going to show you in the table function about how to write these numbers out quickly and easily. So off to your calculators. Here's one I prepared earlier. So just shuffle that over. All right, so if in your graph function, put y equals x cubed, and then back to menu, go into the table function. That's if you're on Casio's. Your x cubed has carried over. So we talked about we want it to work it out at those 0.5 increments. So we need to set the table to do that. So the instructions over here, 4 rectangles, width of 0.5. Set, so it's F5. We want to start at 0 and end at 2. So input those. And each step is that 0.5 increment. So 0.5, execute, and hang on, go to table. So sorry, you were in set, and then we want to get to the table. So we'll exit out again and go to table. Here we are. So when x is 0, y is 0. Remember we talked about when x was 2, y would be 8. So copy that table down each time into your setting out, and that saves you thinking about some of the calculations. So going back to learn how to set this out now. So the next one along, here we go. So there's that table that we've just done on our calculators. Now I want to show you how to set this out. So for the upper rectangles, let's do that. So capital A subscript U. Now, as we said, we've got the width of 0.5 each time. So another way that we could do this, a little bit more efficient, is you take out that common factor of 0.5 and put it out the front. And then what you're working out is the heights of the 4 rectangles. And so our first one is f of 0.5, then f of 1, etc. So let's write that out. Feel free to speed this up if you need. Slight light here there. The first one is 0.5, as I said, not 0. And then f of 1, then f of 1.5, and then f of 2. So there are 4 rectangles. They're the heights of them. And feel free to just write that and then skip to the answer, but I want to show you all the setting out. So f of 0.5. You come across to your table here, and the y value, which is going to be your height, is 0.125. So writing that down, adding on f of 1, where you've got your table here, f of 1 is 1. So that's 1 cubed. And then adding on the other 2, and finally f of 2 is 8. Working that out, I'll tell you it's 6.25. So there are upper rectangles and our lower rectangles now. So 4 rectangles with width of 0.5, and this time round we're going to be having f of 1.5 will be our highest, down to 1.5 and 0. Now, as I said, you don't have to show that 0 one if you don't want to, but I find it's a really handy habit to get into as a cross-check for doing 4 rectangles. And then we use our table. F of 0 is 0, so we'll put 0, adding on f of 0.5, 0.125, f of 1, and f of 1.5. You'll notice that the middle 3 each time get used in both the upper and the lower, and the ones on the extreme only get used once. That's exactly what's supposed to happen. And then the calculation for that is 2.25. So the official answer that we write for this then, if I can fit it on my iPad, is the actual area is, and we write it as an inequality, 2.25, capital A for area, between 6.25 of x cubed for what have I got here? 0 between 0 and for x between 0 and 2. So that's technically how we write it out. And just one more here. If you get a question like this is a past exam question. Considering a function here, 10 on x squared, here's the graph. Now notice that this one's going, well, not only is it decreasing, but you'll notice something with how the rectangles fall. So you'll often get asked to draw on the upper and the lower rectangles. So initially they want us to represent the overestimate, so the upper rectangles, between 1 and 5 using 2 rectangles of equal width. So think about that, between 1 and 5, we want 2 rectangles, so the width will be 2 this time round. So thinking about that, if you want an a rectangle, here's your base, what's the height of that one going to be? Well, it has to be overestimate, so the rectangle is going to go up this high, and it's going to be over here. So you draw that. You don't have to draw the base because the axis counts as the base for you there. So you'll end up drawing 3 lines, obviously using a ruler, and the second one will be here. So where that hit the function there at 3 and across to 5. It's just that the point of interest is on the left-hand side for the upper rectangle this time. See, on the left and on the left. Whereas the previous one we did, it was on the right. So you've just got to be on the lookout for that. It's not going to be the same every time. There's 2 options. And if we were asked to draw the lower rectangles on this graph as well, the lower rectangle would hit here. I use different color, and at 5. So you go up until it hits there. Okay, so that's how you draw the rectangles if you get asked. So that's the end of this video. If you liked it, give it a thumbs up and subscribe to the channel. And the next video in this series for my class is in a separate chapter, but it's the area under a curve. Thank you.